Hello everyone! Did you know that 24% of the total energy of the universe was occupied by so-called dark matter, which we don't know what it is. 24% of the universe is something we have no idea what it is. Maybe people ask, Tom, how do you know that there are dark matter? Today, I'll give you 3 evidence of the dark matter. Let's get started. The first one comes from galaxy rotation curve. We live in this galaxy, so-called Milky Way galaxy, and this Milky Way galaxy is rotating. And then, if you look at the rotation curve here, this is showing a rotation curve of the Milky Way galaxy. And this is the distance. Milky Way galaxy is a spiral galaxy like this, and this distance from the center. And this is the rotation speed. And then if you look at the data point here, so rotation speed is not so fast at the center of the galaxy. If you go outside, it gradually gets faster and it flattens out in the outskirts of the Milky Way galaxy. So this is what we know from observation using telescope, we know that. But what's surprising here is we also know how much stars are in our Milky Way galaxy. By taking picture, we know how much stars are in Milky Way galaxy. And if you calculate the gravity from those Milky Way stars, then rotation velocity expected from these stars are only like this. It should slow down outside of the galaxy because there are not many stars in outside of the galaxy. If I take this mouse, right, and then if I do this, the mouse is not going to fly away because mouse is pulled by this string. It's tied by this string. If there's no string and the mouse is moving very fast, and then if I cut the string, the mouse is going to fly away, of course, right? But it doesn't fly away because of the string, pull from the string. In the case of the galaxy, this pull is gravity. The gravity from the Milky Way galaxy here. But in the observational data, Milky Way galaxy is rotating so fast in outskirts. This is almost 200 kilometers per second. And then such a fast rotation, but those stars do not fly away from Milky Way galaxy. That means there's a strong gravity there, even outskirts of the Milky Way galaxy. And this gravity is not from stars because we know there are not many stars in this outside of the galaxy. So there must be some matter, a lot of matter is affecting the gravity to support this fast rotation. This matter is so-called dark matter. So in outskirts of the Milky Way galaxy, there are a lot of dark matter to keep these stars, fast-moving stars, not fly away. Fast-moving stars and gas not to fly away. So this is the first evidence of the dark matter. Here's a simulation, okay, of dark matter-less Milky Way galaxy and Milky Way galaxy with dark matter. With dark matter, the outskirts of galaxy can still rotate very fast. But without dark matter, outskirts the gravity is weak, so the matter can rotate very slowly only. If you compare the speed here and speed here, it's moving faster with dark matter, right? And then in our reality, this is the case of our Milky Way galaxy. So that's how we know this dark matter. If someone asks you to draw a picture of a spiral galaxy, you might draw something like this. This is what I drew. This is only 10% of the Milky Way galaxy. The 90% of the mass of the Milky Way galaxy is in the so-called dark matter halo surrounding the Milky Way galaxy, way behind the optical part, the bright part of our Milky Way galaxy. This bright part is only 10%. 90% is dark matter, which is invisible to us, but it has strong gravity, so we know it's there. Let's move on to the second evidence. Second evidence comes from the galaxy clusters. galaxy movements in galaxy clusters. So this is a typical example of a galaxy cluster. Galaxy cluster consists of thousands of galaxies, so there are two big galaxies inside. These small individual ones are galaxies, and all of them at the same distance making one big group called galaxy cluster. And this Dr. Fritz Zwicky, he's, by the way, the one who named dark matter as dark matter. He was investigating the velocity of these individual galaxies in cluster. By measuring the velocity of individual galaxies in cluster, we measure the mass of the galaxy cluster. If the mass of the galaxy cluster is very large, galaxy can move very fast because gravity can keep the fast speed of galaxies. If gravity is weak, then galaxy can move very slowly, because if you move too fast, you jump away from the cluster. So to stay in the cluster, you need to move very slowly. So which was the case for this galaxy cluster? Here, Dr. Zwicky measured the velocity of galaxies, and in average, their velocity was 900 km per second. This is very fast speed. And if you calculate the mass of the galaxy cluster based on this number, he got this: 2 times 10 to the 15 solar mass. Solar mass is the mass of our sun. So the galaxy cluster is 2 times 10 to the 15 times more massive than our sun. And then if you compare this mass, so this is so massive, compared to the amount of stars in galaxy cluster, the stars, if you take a picture and weigh stars in galaxy cluster, the total mass is 3 times 10 to the 13. So you notice this matter, all the mass in galaxy cluster is 100 times more than the mass in star. Again, this is because of the dark matter. It's invisible here, but 100 times more mass are in this dark matter in galaxy cluster. So that's the second evidence of the dark matter. Let's move on to the third evidence of the dark matter, so-called gravitational lensing. Okay, so this is a typical example of gravitational lensing. So there's a massive galaxy cluster. Those orange-ish galaxies are at the cluster, and then those arc-shaped galaxies are more distant galaxies behind the galaxy cluster, but its shape is bended by the gravity of the galaxy cluster into this arc-like shape. Here's a schematic view graph. So here's a galaxy cluster in front, and then here's a galaxy behind. And when the light from this distant galaxy comes to the Earth, this light is bended by the huge gravity from the galaxy cluster. That's why it looks like arc shape. This is called gravitational lensing. Well, Einstein's general relativity predicted gravity can bend the light. So this is also proof of Einstein's general relativity. By the way, very useful way to use this is we can use this gravitational lensing to measure the mass inside. In a very simple form, if there's more mass, this arc is far away. If there's less mass, this arc is closer to the center of the gravity. And in this case, this arc is very far from this galaxy to the center, from the center of a cluster. So that's why we know there's a lot of mass in this galaxy cluster. If you do the calculation, there's again gravitational lensing suggests about 10 to the 15 solar mass in this galaxy cluster. This is again 100 times more mass than in the stars in galaxy cluster. So adding all the stars here, all of them is 10 to the 13. But gravitational lensing indicates 10 to the 15. So again, there should be dark matter in galaxy clusters. Okay, so this is how we know 24% of the universe, energy budget of the universe, is dark matter. We know dark matter is there because we can measure the gravity because there's a gravity from it. But dark matter do not emit light, that's why it's called dark matter. And the problem is, even though it's occupied 24% of the energy budget of the universe, we don't know what is dark matter. It's remaining mysteries of the universe. If you can figure out what is dark matter, I am sure that you will get a Nobel Prize. See you next time.